In this video, we will talk about testing multiple linear restrictions using the f-test. Now, remember that when we use the t-test, that was allowing us to test whether a particular variable xj had no partial effect on y. So when we set up that null hypothesis that said beta j is equal to 0, we were testing the partial effect that xj has on y. So sometimes we might encounter situations where we want to test more than one hypothesis, which involves multiple population parameters. So here in the t-test example, we only have a single population parameter that we are testing this hypothesis about, but when we talk about the f-test, or when we test, we want to test multiple linear restrictions, we are talking about more than just beta j. So there could be two or more beta j's that we are interested in. Okay, and generally, when we are talking about testing multiple linear restrictions, it is not valid to look at individual t-statistics. What we need is a statistic that tests for a joint multiple hypothesis, or tests for joint significance. And this is best explained if we take an example. In this example, we will use the MLB1 dataset from the Woolrich package in R to take a look at what are the factors that determine Major League Baseball salaries. So we have data on players, and on the left-hand side, we have our dependent variable, which is log of salary. Okay, so this variable is already created in the dataset, and we want to explain this dependent variable. So you can imagine that there are some variables on the right-hand side that might help us understand this dependent variable. So we have years, and years is the number of years that a player has played in the league. Then we have games year, which is the average games a player has played per year. Then we have some performance metrics here, which is giving you the career batting average of the player, the home runs per year, and the runs batted in per year. So all these three variables are performance metrics. Okay. So let's say that for our null hypothesis, after we have controlled for years and the number of games per year that are played, we want to test the hypothesis that actual performance, or these three performance metrics, have no effect on salary. So in effect, what we're saying is, if we set up our null and we write out our null, these population parameters, beta 3, beta 4, beta 5, are jointly 0. Okay, so this is how you can write out the null hypothesis. Okay, so again, actual performance has no effect on salary. This is what we're trying to say in our null hypothesis after we have control for the number of years and the number of games played per year. And these are also called exclusion restrictions. This would make more sense later, but the idea here is that if this null hypothesis is actually true, then we can exclude these three variables from our regression analysis, or from this equation that we wrote here. Now, to test the null that we set up, we actually need a joint or multiple hypothesis test. And the t-test can't do that, okay? So remember, we said that the first step is always to set up your null. The second step is to specify what your alternative is. And in this case, the alternative hypothesis basically says that the null is not true, okay? In other words, we can specify the alternative by saying that at least one of beta 3, beta 4, or beta 5 is different from 0. Okay, so any of these or all of these or some of these can be different from 0, and that would be our alternative hypothesis. Now, when we are dealing with the F-test, one-sided alternatives are hard to deal with. So we will just deal with the case where our alternative is two-sided. And we will take a look at when we estimate this model, what happens. So here is our output. So what we've done here is we've regressed log salary on all those variables. And remember, the performance variables are, performance metrics are these three variables for a player. So batting average, home runs per year, and RBIs per year. Okay, so runs batted in. And notice now that we understand output, here are our p-values. If we want to look at which of the variables are individually significant, right? Whether you want to look at the t-statistic or the p-value, each software is going to tell you by giving you some indication of the significance here. So you can see there are significance codes that the stars indicate at the different significance levels and which variables are significant for our dependent variables. So here we can see that years, the number of years the player has played in the league, and games per year are significant. But then we see that these three performance metrics are individually insignificant. Okay, so this is concerning, and this might make us question whether we need to change the model or drop these variables. And this is when we can try to incorporate an F-test, which is going to test whether these variables are jointly significant for our for log salary. Okay, so another thing to notice here is that R sometimes would report these numbers that sort of look odd. So here, if this says 6.886 E minus 0.2, this is to be interpreted as 6.886 times 10 to the negative 2. Okay, so you can interpret this as 0.06886. Okay, and that's how that number would be interpreted. Typically, you would not have this, but here it seems to me that there are some numbers that have a lot of decimals, and that's why R is reporting it this way. Okay, so if we want to look at the effect of batting average, for example, this is a really small number, right? So this is saying it's 9.786. 9.786 times 10 to the negative 4, right? And this is a very, very small number. And this is not very large, right? So that's what it's telling us. We can also use the equation to answer questions like how much is a solo home run worth or what is a grand slam worth. But that requires more information on baseball, and I'm not assuming everybody's a baseball fan. But you can answer different questions, but we want to get to the F-test, so let's talk about that. So, like I said before, on the basis of these three insignificant t-statistics or p-values, the question for us would be, should we conclude then that none of these performance statistics actually affect baseball player salaries? Okay, the answer is no. And that would be a big mistake for us, okay? The problem is sometimes related to multicollinearity. So if you look at the correlation between home runs per year and RBIs per year, the correlation is very high, to the tune of 0.89, right? So almost 0.9. And what this problem can do. What does that mean for the variance of our estimators, and what does that mean ultimately for statistical inference? So remember why we get this correlation to be high, and why are we even testing this correlation. So remember that in baseball, you can't hit a home run without getting at least one RBI. And typically, home run hitters also tend to produce a lot of RBIs, right? So it's almost intuitive that the correlation would be high. And that would make the sometimes the t statistics insignificant. Now, because these individual coefficients are imprecisely estimated because the variance of our estimators are high, we can rely on some sort of a joint test. Okay, so when we start constructing the F-test, we want to talk about two models. One model is called the unrestricted model, in which we are going to include all our variables just like we had before. So we have the first two variables, years and games year, and then we have the last three variables, batting average, home runs per year, and RBIs per year. So this is, we're going to call this the unrestricted model, and we are going to abbreviate that with UR, okay? So the other model we want to talk about is called the restricted model, and the restricted model is going to exclude, remember the exclusion restrictions we talked about in just a few slides earlier. We will exclude these three variables, okay? And we will write out our model, which is a restricted model now, just with these two independent variables. So what the F-test is allowing us to do is to see how the fit of the model deteriorates as we move from the unrestricted model to the restricted model. Okay, so as we remove these variables, these three variables, what happens to the fit of the model? Okay, if nothing happens, then we are okay dropping the three variables. But if something changes, then we might have to keep those three variables because they jointly contain some information about log salaries. Okay, so let's talk about some notation here. Let's say that the sum of squared residuals from our unrestricted model is denoted by SSRUR. Okay, and in this particular example, the degrees of freedom can be calculated for the unrestricted model. So let's say we had 330 players and we are estimating 6 estimators. So 5 variables plus 1 intercept. So we have 324 degrees of freedom. And then we are saying that let the sum of squared residuals from our restricted model be represented by SSR. And in this case, the degrees of freedom are going to be just 330 minus 3. Okay, so we have 2 slope coefficients and 1 intercept. Okay, so in this case, the degrees of freedom is a little bit higher, which is intuitive because we did not estimate 3 other slope coefficients. Now, our intuition tells us that when we compare the sum of squared residuals from our restricted model to the sum of squared residuals from our unrestricted model, there is going to be this inequality that will hold. Okay. So as we add the number of variables, as we add more number of variables to the right hand side to our regression, the sum of squared residual typically drops, and that's why you have this inequality. So then what are we doing once we have these two types of regression set up? We're asking that does the sum of squared residuals increase proportionately by enough to conclude that the restrictions under the null hypothesis are false. Okay, so in other words, we are basically trying to ask the question, that is there a significant change in moving from the unrestricted model to the restricted model? Okay, so this is what we are trying to ask. Is there a significant change between this? Okay. So here, the null hypothesis in a more generic sense can be written as the following, where we are excluding Q beta J's. Okay, so in our case, in our baseball example, we are excluding 3 beta J's, right? Beta 3, 4, and 5. But in general, you can write it out this way. So Q is going to be the number of exclusion restrictions that we are imposing. So this brings us to the F statistic. And the F statistic uses some sort of a degrees of freedom adjustment. So let's take a look at what this is saying. So in the numerator, you have this term which says the F statistic contains the difference between the sum of squared residuals between the restricted and the unrestricted model. And remember, we said that the sum of squared residuals from our restricted model is definitely greater than the sum of squared residuals from our unrestricted model, right? So this value is going to be positive. And the degrees of freedom from our restricted model are going to be higher, right? This is also higher than our unrestricted model. So we are basically dividing the numerator with the difference between the degrees of freedom. And if you simplify this, this just becomes Q, right? So this is just how many variables or how many population parameters are we dropping, okay? So what is the number of exclusion restrictions in other words, okay? So that's what we have in the numerator. And in the denominator, we have just the sum of squared residuals from our unrestricted model divided by the degrees of freedom from our unrestricted model. Okay, so if you were to write this out, this remains the same, but this is just divided by Q, and this is divided by n minus k minus 1. Okay. Now, it's important for you to know that the F statistic is usually going to be non-negative and almost always positive because of the way the formula is set up, okay? And the computer can compute this for you, this F statistic for you. Now remember, when we are trying to test hypothesis, the third part was to go and get the critical value for the test. So once we have the F statistic calculated, we can obtain the critical value from the tables, okay? And in softwares, I'll show you how to do that in R. But basically, we can go to the F tables. And for that, we will need what the degrees of freedom are and what is the number of exclusion restrictions in our model, okay? And the level of the test, significance level, okay? So here's a probability density function that's showing that Q is equal to 3, and let's say this was the degrees of freedom from our unrestricted model was 60. Okay, so you can go check the tables, and this is going to show you that the 5% critical value is 2.76. Okay, so then the rejection rule is basically going to say that we are going to reject the null when the F statistic exceeds the critical value. So in other words, if the F statistic is greater than 2.76, we can reject the null that the performance metrics are jointly equal to 0, which would mean that we need to keep those in our regression, right? Because jointly they add some value, because we are rejecting the null in favor of the alternative. Okay, so now if we look at the F statistic for our example with baseball, the F statistic is 8.34, okay? And it is above the 1% critical value of 3.78. So we can conclude that we can infer that we should reject the null, that those performance metrics are jointly insignificant. Okay, and in R, we can carry out the test in a very, very easy way. So we can write out what our unrestricted model is, right? So this is with all of the variables. And then we can set up our null hypothesis. We can just call it my H naught and specify the variables that would be a part of the exclusion restrictions. And then we can use the linear hypothesis function, which comes from the car package, by specifying two things. One, the regression, which is unrestricted, and also what are the exclusion restrictions, okay? So notice here, when you look at the output, it says this is what we are testing. We are testing that these are jointly 0. The performance metrics are jointly 0. And here we can see that our F statistic is 9.55, and the probability, the p-value, is telling us that this is significant, right? So this means whenever this happens, the F statistic is greater than the critical value, or the p-value is significant, we basically reject the null in favor of the alternative. Okay? So you can calculate the F statistic different ways, but I like to calculate it using Rsquare, because Rsquare is what's reported in the restricted or the unrestricted regression. But the sum of squared residuals, in case you know that, in case you want to compute that, you can also do it by hand. Okay, so here the F statistic is computed by hand, but we don't have to do it this way. Okay, now you can read some of these slides, but basically the idea here is that we typically should not try to use the F statistic when we are only trying to drop one variable from our regression, right? If you just are trying to test whether you should keep one variable or not, then you should just rely on the T statistic. So you should not use typically the F statistic for a single exclusion restriction. You should use it for two or more variables. It can also be shown that when Q is equal to 1, when you're trying to drop just one variable, that the F statistic is just the square of the T statistic. Okay, and this happens because if you square the T distribution, this is identical to this F distribution with one exclusion restriction. Okay, so I particularly like the t-test, and it's more transparent and allows also for the one-sided alternative. But the f-test is not going to add much if you were just dealing with one exclusion restriction. Okay. Now it can happen that if you had a model like this, for example, and you were trying to test whether beta 2 and beta 3 are jointly significant, right? So if you're setting up this null hypothesis, which says beta 2 is equal to 0 and beta 3 is equal to 0, and if we apply the F test after knowing that beta 2 hat is statistically significant, so this one beta 2 hat is significant, but beta 3 hat is not, then you might actually find that the F test may not reject the null, okay? So generally, if you use an F test for variables that are significant with a bunch of other variables that are insignificant, if you're looking at those variables individually, it has less power than a single t-test. That's just something you want to keep in mind. Now, like I said earlier, F statistics are easier to compute when we take a look at the regression summary and we look at the R-squared from our regression. Okay, so here we have sum of squared residuals that can be written in this form. This is just coming from your previous chapters. Okay, so if we make those substitutions in the F statistic formula, we will find that the F statistic can be written in this form, where in the numerator we have the difference. Now the difference is between the R-squared, which is going to be higher for the unrestricted regression, minus the R-squared from the restricted regression, and in the denominator you're going to have 1 minus R-squared from your unrestricted regression. Okay, and the exclusion restrictions remain the same, and the degrees of freedom in the denominator remains the same. Okay, so the F statistic is going to be greater than or equal to 0, and that's the idea of it. Okay, so in the lab we're going to see how to calculate that using R-squared. And finally, the F statistic that is reported in the regression summary that you see in R or any other software is a special case of a null hypothesis. Okay, so the F statistic that is actually reported is not the F statistic that we had computed using the linear hypothesis command. Now, if we had a model like this, if we set up our null hypothesis, which says that all of our slope coefficients, right, all the slope coefficients, so all of the coefficients that are attached to the x's or the independent variables are jointly equal to 0, this would, if we are testing this null hypothesis, we can do so by using the F stat that is reported in our regression summary. Okay, and typically we're always going to reject it. Okay, so if you want to go back and see what that is, let's take a look at our regression from before. So this was our regression from before, and notice that there is an F statistic that is reported here, and the p-value is really small, right? This is e to the minus 16, which means 2.2 times. This is 2.2 times 10 to the negative 16, which is a very small value for p. And so we can definitely reject the null that all these variables are jointly significant. Okay, so that's the idea here, if we were trying to interpret that F statistic. But that's not much use to us. Okay, so that's the idea here. And yeah, so you can read the rest of the slides, but what we'll be left with is from our regression output, we will interpret what is the adjusted R-squared, or the if you spell it out, it's the adjusted R-squared, but it's reported like this in R. We will talk about how that is a goodness of fit measure in later chapters.